Hi guys, today we're going to be talking about basalts and the mantle. So let me just jump right into why basalts are important. And it's in the fact that the composition of basalts, both major and trace element composition, as well as isotopic compositions of basalts, provide direct information about the nature of the composition of the mantle, as well as its structure. And so today we'll be talking about the structure and composition of the mantle based on that of basalts, because we can't directly sample the mantle, so we have to rely on the information provided in basalts. And then we'll also talk a little bit about the partial melting processes in the mantle that form basaltic magmas, which we can basically recreate or reconstruct those processes and understand those processes because of all the information within basalts. And it's also important to note, if you're unaware, that I don't know the exact percentage, but I want to say like 75% of Earth is covered in oceanic crust, and oceanic crust is basalt, guys. So everything coming out of mid-ocean ridges is basalt. The continental crust is not basaltic, but it's a minor component of Earth compared to oceanic crust. So that's another reason why it's really important that we understand basalts and use them to understand Earth's mantle and the rest of Earth's interior. Now I'm going to get into in a couple slides what Earth's interior looks like. So the core, the mantle, everything, and the parts of the mantle and how thick they are and how dominant they are within Earth, because they are. But first I want to discuss the two major types of basalt. These are alkali basalts and tholeiitic basalts. Now, all basalts are fine-grained extrusive mafic igneous rocks, but alkali basalts and tholeiitic basalts differ in their compositions, and we can understand how their compositions differ by looking at this basalt tetrahedron over here to the right. Now, this is a pretty busy tetrahedron, but guys, I just want you to focus on two major planes. These two planes include one, the olivine, albite, and augite plane, as shaded here in yellow, and sometimes books use clinopiroxene up here at the tip of the tetrahedron, but augite is a clinopiroxene, so same difference. If your book says that, go with that. But it's this augite slash clinopiroxene, olivine, and albite plane that differentiates alkali and tholeiitic basalts. As we can see, alkali basalts lie on the nepheline side of that plane, whereas tholeiitic basalts lie on the quartz side. But with tholeiitic basalts, there is another plane to consider, and this is the hypersthene, albite, and augite plane. And again, sometimes books have the hypersthene labeled as orthopyroxene and the augite labeled as clinopiroxene, in which case it would be the orthopyroxene, albite, clinopiroxene plane. Both cases are correct. So that is the plane that differentiates more olivine-rich tholeiitic basalts and more quartz-rich and olivine-poor tholeiitic basalts. And these planes are called the plane of critical silica undersaturation for the first one, and the plane of silica saturation for the second one. And so what does all this mean? What are the actual differences between alkali and tholeiitic basalts? Well, there are differences in their chemical composition. The alkali basalts contain more alkalis, aka sodium and potassium oxides, as we discussed in the chemistry of igneous rocks video, and tholeiitic basalts contain less alkalis, and therefore in the alkali-lime index are classified as calcic or calc-alkalic rather than alkalic or alkali-calcic as the alkali basalts would be. But alkali composition is not the only difference between the two. Silica content is also different. There's more silica, especially in the form of quartz, in tholeiitic basalts than alkali basalts. And lastly, incompatible elements such as rare earth elements, titanium dioxide, and phosphorus oxides in alkali basalts than tholeiitic basalts. But what do all these chemical composition differences manifest as when it comes to looking at the actual rock in a hand sample or thin section? Well, for example, olivine is present only as phenocrysts, as shown here in this hand sample and here in this thin section, in tholeiitic basalts, whereas in alkali basalts, it can be phenocrysts or present in the ground mass. If you don't remember what phenocryst means, you can watch the igneous rock textures video where I talk about all those different textures, but phenocrysts are just big clasts in the rock, whereas ground mass is obviously the rest of the mass of the rock. So olivine is present as big class in tholeiitic basalts, and it does not show up in the ground mass as opposed to an alkali basalt. It can be present in the ground mass. Additionally, pyroxene and plagioclase ground mass is present in tholeiitic basalts, and alkali basalts can also have this, but alkali feldspar is potentially enriched in the ground mass of alkali basalts, whereas it is not in tholeiitic basalts. And pleochroic augite is present in alkali basalts, whereas only colorless augite is present in tholeiitic basalts. If you don't remember what pleochroic means, it just means it changes color when you turn it under polarized light. And we talked about that in the optical mineralogy video if you want to check that out. And lastly, silica is present as quartz in the ground mass or glassy matrix or even lining vesicles in tholeiitic basalts, whereas nepheline is present as residual glass or ground mass in alkali basalts. And now you might actually be remembering that in our phase diagrams video, we talked about how nepheline and quartz are chemically separated by albite. So we've got this separation here of albite in between the two compositions of silicate minerals, quartz on the right and nepheline on the left. And because of this, melts on the silica side of the diagram evolved to the quartz-bearing eutectic. So the quartz and albite shared eutectic on the right side of this diagram. And this eutectic composition is defined as tholeiitic, whereas those on the nepheline side of the diagram will evolve to the nepheline albite shared eutectic, and this eutectic composition is defined as alkaline. So there is the major difference where we first defined what the difference between tholeiitic and alkaline is in that phase diagram video where we talked about the quartz nepheline diagram. This is where all their chemical differences stem from, and this behavior extends to their differentiation. We talked about magmatic differentiation in the silicate magmas video, and in the case of tholeiitic melts, they differentiate toward silica saturation, whereas alkaline melts differentiate toward nepheline saturation. And the rocks that result from alkaline and tholeiitic melts respectively are phonolite, which is the alkaline extrusive rock, as well as its intrusive equivalent nepheline syenite, and trachyte, which is the extrusive tholeiitic rock here and its intrusive equivalent syenite. The ones on the left here contain nepheline and no quartz, and the ones on the right contain quartz and no nepheline. So now that we've discussed the two major types of basalts and their compositional differences, let me jump into discussing a little bit about the mantle, the Earth's interior, how much of it is the mantle, and how we can use these basalts to understand the structure and composition of the mantle. First, like we've been discussing, because basalts are partial melts of the mantle, and I'm going to get into a little bit more how partial melting in the mantle works later in this video, but if you want to know what partial melting is in general, we discussed that in the silicate magmas video, so you can check that out. But because basalts are partial melts of the mantle, meaning that they give us a little bit of the mantle in their composition, but not all of it, we can get some insight into the mantle's composition if we understand the melting and crystallization processes happening in order to form those basalts. But it's important to note that basalts are not the only thing that we can use to understand the composition of the mantle. We can also reconstruct the composition of the mantle by directly looking at rocks that represent the mantle's composition. These rocks are rare, but they come up to the surface occasionally as xenoliths or ophiolites. We talked about xenoliths in the plutonic igneous structures video if you want to check that out, but they're basically just clasts of different surrounding rock that can be ripped off and incorporated into magmas that are crystallizing either below the surface of the Earth or magmas that are rising and coming out of mid-ocean ridges and are going to cool as basalt might incorporate xenoliths in their structure. But the major thing that's important here is that xenoliths can be clasts that represent the composition of the mantle. Likewise, ophiolites or ophiolite suites are pieces of upper mantle and oceanic crust that have been thrusted up onto continents by tectonic activity. And these can be really valuable in understanding at least the upper mantle's structure. Another thing that can be useful though are chondrites. Chondrite meteorites are stony meteorites that represent a composition similar to bulk Earth. Now, bulk Earth is basically the composition of Earth if it wasn't all layered and separated out. If you mixed it all together again like it was in the very beginning of its formation, it would be similar to these chondrite compositions. And because chondrites represent bulk Earth composition, if we subtract the core and the crustal compositions from the bulk composition of that meteorite, we get something analogous to mantle composition. Lastly, I've talked about 3 things that help us understand mantle composition, but none that help us understand necessarily mantle structure. So what helps us reconstruct and understand mantle structure? Well, this comes down to geophysics, and that is mantle density and seismic velocity, which we can measure with amazing tools that we have today, can provide us information about its structure. We can tell what kind of seismic waves travel faster or slower at different parts of the mantle, giving us information about its density and structure. But how far down does crust go? And where does mantle start? And then where does core start? How much of Earth is mantle? Well, short answer is a freaking lot. But let's go through systematically what Earth's layers are composed of and how thick they are. The first one is oceanic and continental crust. The outermost rocky surface on Earth, you could argue, is continental crust, because that is the type of crust that, forms mountains and is higher in terms of elevation than the oceanic crust. The oceanic crust is not only lower in elevation and doesn't protrude out as much as continental crust, but it's also much thinner. We can see that here in this figure. While continental crust can get up to 70 kilometers thick, oceanic crust is only about 7 to 10 kilometers thick. Below Earth's crust, this dark brown layer is the lithospheric mantle. So if you've heard the term lithosphere, it's not a synonym to crust. The lithosphere refers to the uppermost lithospheric mantle as well as the continental and oceanic crust. And the reason that we don't just say, okay, all of the lithosphere is now just defined as crust is because there's a major discontinuity between the crust and the uppermost lithospheric mantle. And this is known as the MOHO discontinuity. I won't get into detail on this right now, but basically it just represents where seismic waves increase in velocity. However, below this layer is the contact between the asthenosphere and the lithosphere. And yes, both are still technically upper mantle. But the difference between the asthenospheric mantle and the lithospheric mantle is that the lithospheric mantle deforms brittly and the asthenospheric mantle deforms more ductilely. And again, we know about this structural difference between the asthenospheric and lithospheric mantle because of seismic wave velocity measurements. The next layer is the transition zone. This is kind of the middle mantle, you could say. And then the final layer of the mantle is the lower mantle. Then we get to the core, which has the outer core and the inner core. But the major takeaway here is that the mantle, in all of its forms, the uppermost lithospheric mantle, the asthenosphere, the transition zone, and the lower mantle, comprise of a heck of a lot of Earth's interior. So what is it exactly, though? Well, under normal circumstances, the mantle is solid, and it actually has to undergo melting to then induce magmatic and volcanic activity that forms the igneous rocks that we know and love at Earth's surface. But there are specific instances or phenomena that can generate melting, and these include 3 major ways that the mantle can undergo melting. The first way is that the normal geothermal gradient could be perturbed or disturbed in some way that causes a local hot spot in which melting occurs, such as Hawaii, for example. There's a hot spot there. That's why you have the Hawaiian Islands, and that is because way down deep in the mantle under there, there's some sort of perturbation in the normal geothermal gradient causing melting in the mantle. This eventually manifests itself as volcanic activity at Earth's surface, causing the formation of such islands. The second way that melting can occur in the mantle is by melting temperatures of the mantle's material becoming lowered by the addition of volatiles such as water or carbon dioxide to the dry layersolite, which layersolite is just the rock type that the mantle is. And we'll talk about that and why we know that in a second. But If you add water, for example, as subducting oceanic plates do when they go down and subduct into the mantle, then the melting temperature is lower and the mantle begins to melt, and that induces the magmatic and volcanic activity that we see at subduction zones. And lastly, the third major way that the mantle can melt is by decompression at divergent plate boundaries such as mid-ocean ridges, where ascending mantle material goes up and is decompressed, the pressure decreases, and that induces the melting of the mantle and therefore the magmatic activity and extrusion of this magma at mid-ocean ridges. So when mantle melting is induced by one of the three processes we just mentioned, what composition results from this melting? Well, the composition of partial melts of the mantle can be plotted by this diopside, forsterite, instantite ternary phase diagram shown here on the bottom of the slide. Upon heating, larzolite, which again is the composition of the mantle, begins to melt with the composition X, which is the eutectic composition in this ternary phase diagram. As the larzolite melts at the eutectic composition, it decreases the leftover solid in diopside and instantite and increases the leftover solid in olivine. Remember, forsterite is olivine. And this olivine-rich residual solid will be the last thing to melt. If everything melts, then we might be able to get some olivine-rich stuff to melt and then rise and then come out at the surface. But typically, everything but the olivine stuff melts. And that's just because it requires really high temperatures. And so generally, basalts, which are results of partial melting of the mantle, leave the mantle enriched in olivine. And I kind of put an equation here that is the mantle, which is larzolite, minus basalt, which is the result of partial melting of the larzolite mantle, equals peridotite, which are olivine-rich rocks such as Harzbergite, which is a peridotite that contains little to no clinopyroxene such as diopside, and dunite, which is a peridotite that's almost purely olivine with only minor to trace amounts of orthopyroxene and clinopyroxene. So getting back to the rocks that result from such partial melting of the mantle, such as tholeiitic and alkali basalts, one major question remains, and that is, how does melting of the mantle, that is all larzolite, produce compositionally different basalt types, especially when we just saw the ternary diagram that showed a pretty clear picture of how partial melting affects the larzolite mantle? This comes down to the source debate. This is the debate regarding what magmatic source alkali basalts come from and what magmatic source tholeiitic basalts come from, because some people think that because they're systematically different in composition, that means there's two different sources of these two different basalt types. And this would explain the more heterogeneous compositions observed in alkali basalts versus the less variable compositions observed in tholeiites. But there's growing evidence that it's not a different source. It's actually the same magmatic source that causes both types of basalts, but alkali basalts form by relatively lower degrees of partial melting and or melting under higher pressures. So whether they come from the same source and just form by different melting processes, or they come from completely different sources, is still a topic of debate. But regardless, both types of these basalts help us greatly in understanding mantle composition. The last thing I just want to mention comes back to those mantle melting processes and where those occur. We talked about what kind of processes or phenomena drive mantle melting, but where or what type of environments do these melting phenomena occur? There are four major magma generating environments on Earth, and these include constructive plate margins, such as divergent margins like mid-ocean ridges, where you have the spreading of tectonic plates, where the mantle upwells, it decompresses, and that causes decompression melting. The second major magma generating environment is destructive plate margins, where tectonic convergence causes subduction zones and water-induced mantle melting. Like we talked about, water induces the melting of magma because it lowers the melting temperatures of rocks, and you get this subsequent volcanism at those subduction zones. The third type of magma generating environment is oceanic intraplate regions, such as those overlying hotspots, like we talked about, the Hawaiian Islands and other volcanic islands are formed by hotspots, which are caused by perturbation melting. And the fourth and final major magma generating environment is continental intraplate regions. And this can also be hotspots, but instead of being under oceanic crust, it's underlying continental crust. And these hotspots cause volcanism on continents rather than in the middle of the ocean. And we'll actually be talking much more about these four major types of magma generating environments in the upcoming Igneous Petrology videos. But we're also soon going to start the metamorphic petrology portion of these petrology topics that I'm talking about on my channel. And lastly, for this video, the major reference I'm using is the Essentials of Igneous and Metamorphic Petrology by Ronald and Carol Frost. And this will be linked in my description down below if you want to check it out. I'm also using Earth Materials by Cornelius Klein and Anthony Philpotts, which I don't have with me right now, but it's also a great book for understanding igneous and metamorphic petrology as well as mineralogy. So if you want to check those out, you can check those out as well as other minor supporting references in my description below. And that is it for this video. Thank you guys so much for watching, and I will see you guys next time. Bye.